Hello everyone. Today we shall discuss a little more about the spiral structures and try to understand more about how they are formed and why we actually see stable spiral structure. In the last lecture, we discussed about the stellar orbits and we talked about the orbits which can be looked through the epicyclic approximations and the special orbits which are like almost an ellipse. So it goes around and it just miss to be a closed orbit. So these are like rotating ellipses. So these are the orbits which are important to understand the spiral structures. It's not necessary that this has to be ellipse. This can be a little more complicated orbits, but we'll come back to that later. Now for these orbits, you may imagine that you as an observer is not looking at the galaxy or the star from outside. You are there and you are inside the galaxy rotating with such a velocity, such an angular velocity omega p, such that these ellipses looks like they're closed. So you just rotate good enough amount such that the ellipse, when it comes back, exactly closes. These orbits are called co-rotating orbits, and we call that these orbits because when we go to these orbits, we see these elliptical patterns. We'll call this the speed of these orbits as pattern speed. And just keep in mind, the pattern speed is often written in terms of the angular frequency of certain oscillation, which will come back to what it is, and a quantity m, which tells you how many times when it is doing such an orbit, non-circular orbit. Remember our lecture from last time. If we have a non-circular orbit, we have two radius, R1 and R2. The orbits are usually bound in between these radius if the energy is negative. Now, if I look at an ellipse, you see that this starts from, this must be the R2 for the ellipse. It goes to some R1 here. It goes to R2 again. It goes to R1 here. Again, it goes to R2. So which means in one complete azimuthal rotation, it does the radial oscillation twice. So in such orbits, m will be 2. But this is what we mean by pattern speed. So you can think of complicated, more complicated orbits where the m's will be larger. I'm sorry. Yeah. So the pattern speed is defined this way. M is what I just have explained. Fine. Now we have learned about the density wave theory in these two classes earlier by Vidya. And what he said is that the spiral structures in a spiral galaxy or a disk spiral galaxy emerges because of the crowding of the orbits in a certain regions in the galactic disk. And these we call the density waves, which essentially gives you the spiral structure. So this is the basic idea, so that you have an ellipse here. The next ellipse is a little bit rotated. The next ellipse is a little bit rotated. And this way, if I put in all these ellipses, even through my bad drawing, you can see that there are crowding of the orbits along these directions. Let me remind you that when we talked about the epicyclic approximation, we talked about two frequencies. One is the azimuthal frequency, in which so the guiding center goes around, and another is the epicyclic frequency, where the stars goes around the guiding center. So the frequency in which the star goes around the guiding center, we called it the epicyclic frequencies. And probably you have went through this fact that if I have a rigidly rotating disk, then these two frequencies are related. Kappa is essentially equals to omega. And that's what we exactly saw for the ellipse in the previous slide. Now, let me remind you, this crowding of the orbits means that there will be crowding of the stars, means that there will be more density of stars around these spirals, which also means that the matter density, the mass divided by volume, not the number density, the matter density, will also be more. And what does that give rise to? That gives rise to, instead of a very smooth, constant density disk, I have more densities around these regions, which means, say, if a star is here, it will always try to come to here, or if it's near to the other spiral arm, it will try to go there. And that essentially means that this type of extra density on the disk may actually destroy the spiral structure. So the question that one can ask is the following at this point, that, well, I have these density waves, which is very nice, which explains the spiral structures if I arrange the orbits just the proper way. But if I have the stars moving in these orbits, it will see these excess densities along certain azimuthal directions where the spiral arms are, and it may destroy the spiral arm. So is the spiral arm stable? So that's a question that we have to ask. Now, it's not a very straightforward exercise mathematically. And because of that, I thought that I will take you through the actual mathematics of the linear stability analysis in fluid. And then we'll come back to spiral arm again. Using an easier example, and this is a fluid dynamics example. In fact, in the last class, we talked about the fact that because we don't have enough powerful computers, we cannot look at the orbits of 10 to the 11 stars individually. We do fluid dynamics approximation to stellar orbits. So these stars in this case are like gas particles, and the collection of these gas particles behaves like a fluid element, and so on. And we can do this fluid dynamics approximation and study the stellar structures. So that was what we also talked about last time. The question let us ask now is that how to know if I have created a stellar structure, a fluid dynamic structure, how to know whether the structure is stable under certain perturbation. And now it is very difficult to actually study the structure of the stellar disk. So before we go there, let us study a simpler situation. So we consider that we have a three-dimensional volume which is filled with an uniform gas. A three-dimensional volume filled with an uniform gas. Uniform means the density is kind of uniform. So there can be a radial gradient in the density, but there is no azimuthal gradient in the density. And I mention again that it's a three-dimensional volume which is filled with, unlike the disk of a galaxy, which is two-dimensional. Now, how do I approach to this problem? So first we know that we have these two fluid equations. So one is the continuity equation, one is the Euler equation. I don't need the Navier-Stokes equation here because, as we have mentioned, that the stars do not collide, so we will not have the much effect from the viscous term. Now, if I consider the equilibrium condition, so what is the equilibrium here? The equilibrium will be like the fluid is not moving, the velocity is zero. It has a pressure, which I call P0, and has a density, which is rho zero. So if I put this back in these two equations, here I directly see that V is zero, which means that I just get del rho zero del T equals to zero. So the density doesn't change with time if it is in equilibrium. The mean density doesn't change with time. And then if I put the same thing back in here, the V00 means these two terms cancel out. I just get contribution from these terms. And this essentially is telling you that the gradient of the pressure is balanced by the gravitational force. This is nothing but the hydrodynamic stability equation, which you have used enough number of times, at least when you have looked at the stellar structures. And you remember that the divergence of g0, which is the gravitational acceleration, I can also write in terms of g0 is nothing but minus grad phi, and I take a divergence, I get the Laplacian minus grad square of phi, and that we know the Poisson equation tells me that's 4 pi g rho 0. I'm sorry, so there should be a minus sign here. Okay, now this is the condition for equilibrium. So let us now say that, well, this gas is in equilibrium and then I produce a small disturbance somewhere here. So let me just draw a little bit because I have that option now and show you what it means. So I have this region where the gas is in equilibrium. So it's everywhere, its density is similar. And as I said, that there can be radial gradient of the density, but there is no patches in this region where the density is little higher. And now I say that, well, so this is a region where I have a little overdensity. So I cannot, okay. So this is the overdensity region. Okay. So the density is given by the color of this thing. So this is the overdensity region, and that extra overdensity, which is over the density rho 0, I call rho 1. And obviously, because there is overdensity here, there will be more gravity here. So the pressure term will also change. So I will have a extra excess term P1. And then because there is an overdensity, there will be more gravity here. The gases will try to come towards here. So there will be velocity now, which I call V1. And what I do, I put this back again in these two equations. When I do in the first equation, it looks like this. Remember, V0 was 0. And you really identify that the first term del rho 0 del t is 0, which I have got here. And the rest of the term, if you analyze, you will get this thing. Here we have assumed that the perturbations are linear, which means it's a small perturbation. So rho 1 is much smaller than rho 0. V1 is much smaller than, okay. So V1 itself is small. So V0 is 0. So rho 1 is much smaller than V0, rho 0. So this rho 1 times V1 term, which is small times small, can be neglected. So that term we have thrown out. So I get, out of the density equation, I get this. If I do the same exercise with Euler equation, I will get that. And then whatever I have written here inside this funny closed closed region is nothing but what I have over here. It's exactly the same thing. So that means that this term also goes away. What I'm left with is this equation. So the perturbation equation for the continuity is this, and the perturbation equation, this is the continuity perturbation equation, and this is the Euler equation part of the perturbative equation. We also note that the corresponding equation which is written here for the gravity, I will get a similar thing for the perturbative part of rho 1. So G1 will come from the density perturbation rho 1, and that will be given by this. Okay, so let's move on and try to use these things. Okay. Now, let me remind you of the fact that pressure is nothing but a random force. So if I have a fluid element and if I hold a kind of area in the fluid element, pressure is nothing but the random force which is falling, which is being imparted by the particles of the fluid per unit of this area, right? So let's just keep that in mind. It will be useful for us. Now I have these two equations, which I have written here, and this equation. What I do is I take a del t of this equation and I take a divergence of this equation. Once I do that, I realize that this term, so del t of rho 0 divergence of V1, is exactly the same as this term. So I can replace the corresponding thing from here and put that back in here, and I get this nice equation. So now these two equations of the perturbations of velocity and density is combined in a single equation of perturbation only of the density. You can also write the similar thing for the velocity perturbation, but we are not interested in that right now. And I have done one more thing, which is for an adiabatic gas, I can write P1 by P0. So the change in the pressure by the mean pressure equals gamma times ρ1 by ρ0. And from that, I can define the sound speed using this. So this gives me the sound speed. And so it's the speed of sound in this medium. So remember that sound wave is nothing but a wave caused by the density and the pressure perturbations. So that is what comes from here. And that is Cs square what I have used over there. Now the Cs square can also be thought of. So this is arising again from the density and the velocity perturbations. So we said that the density and the pressure perturbations. And we said that the pressure is kind of random velocities. So this Cs square, it can also be thought of a kind of random velocity, the standard deviation of a random velocity square. So kind of RMS velocity square. That we'll come back to later. Now, this is the equation for ρ1. And we are asking the question here, is ρ1 stable? So as we said that we are doing linear stability analysis, we are asking the question, if I generate a perturbation in a fluid, a density perturbation of ρ1, whether that density perturbation will be stable. So what do I mean by that? Well, I mean the following. So this is just an analogy. So say I have a table and I have put a pencil on its nib on the table like this. And you know that it's a very unstable system. So it's an equilibrium system, obviously, but it's an unstable system. If I disturb it a little bit, which always happens, then this disturbance, which is equivalent to ρ1, will essentially grow and it will fall down. So in this case, any disturbance I produce will create more disturbance, and eventually whatever was the equilibrium will completely get destroyed. So we are asking the question, will for our spiral structures, when we create that nice density wave by rotating ellipses, will that destroy itself? On the other hand, if I have a bowl and I have a small metal ball here, and the stable position is, the equilibrium position is obviously at the bottom of the ball here. If I disturb it a little bit, it will always come back here. And if there is no friction, it will essentially oscillate around this equilibrium position, which is a very nice stable situation. So this is a stable condition. This is an unstable condition. What does it mean? It means that if I want to look for the stability of it, then I want to see when this equation will have a solution for ρ1, which is oscillatory in nature. If ρ1 has an oscillatory solution, then that is this case. If ρ1 doesn't have an oscillatory solution, usually then it has exponential kind of solution, then it is this case. So if I have an exponential solution, either the perturbation, if I produce it, it will essentially grow exponentially large. So it will destroy the structure. There can be another case, so just think about it. Okay, so let's go ahead. So how do I study the stability of this equation? So this is stability of the system. So this was the equation. So what I do is I assume that this equation have a solution like this. So this is just a wave solution. Now, I guess at least some of you have done Fourier analysis, and we have also discussed it in the class earlier. Fourier analysis tells you that whatever this rho 1 be, I can always be able to write it in terms of a collection of such waves. And in this case, we are just studying one of these waves. Here, omega is the oscillation frequency of the wave, and k is the wave number. So inverse of k gives you the wavelength. So if I have, so this corresponds to one wave. If I have the x-axis as frequency, this is the wavelength. This is one wavelength of the wave. What this wave has done is has produced excess density here at this region, and it has produced negative excess density here. So this has added up to the mean, which is there, and this has subtracted from the mean. So that's a density wave. So it's also a density wave because the wave is showing you the density perturbation. Now, what did you say in the last slide? We said that if this is supposed to be a stable perturbation, then this rho 1 has to be oscillatory. And when this remains oscillatory in time, it remains oscillatory in time when this omega is a real number, or omega square is greater than 0. So that obviously will depend on the other parameters like Cs and rho 0 in this case. But if I can keep omega square greater than 0, whatever condition it may be, that gives me the stable solution. If omega square lesser than 0, then the perturbation will either grow or die down. So if the perturbation grows, it will essentially destroy the structure, which is the initial structure. If the perturbation dies down, then the perturbation dies down. It's not there anymore. So I have just tried to show it here again. So you have this otherwise rho 0 density. I create a perturbation here. So that the darkness of the thing is kind of the amplitude of rho 1. And in one case, if omega square less than 0, it may grow. So this structure may destroy, and then you may have a smaller structure here because the density falls into here. So this is like what you see, the star formation. Or it may die down where this disperses in the entire volume and eventually you don't see any perturbation anymore. Now, how do I study that? Well, I put this back into this equation. And once you put this back, I have not done this exercise here, but you should do it. So if I put rho 1 back here, I can take the second derivative, I'll get a minus omega square. Similarly, so once you do this, I will get k square from this term, etc. So once you do that, you will get a relation between omega and k, which I have written here. So this is the relation between omega and k, which you get once you put this inside the equation. This type of equations, which relates the omega oscillation frequency. So this is the oscillation frequency. Remember, this is the oscillation frequency that we talked about when we defined the pattern speed. And the wave number, which is how big density disturbance that you have created. These two are related in this equation. This type of equations are called dispersion relations. So these equations are called dispersion relations. The reason it calls dispersion relation is it essentially tells you, given the size of the wave, how fast it will move. Anyway, so that's a different discussion. We will come back to it in the next class again, where we will discuss the dispersion relation of a completely different wave. And we'll see that what is the consequence of that. But remember, omega square greater than 0 for us right now gives the stability. So omega square greater than 0 here means that this right-hand side greater than 0, which tells me that k has to be greater than this quantity. So if k is greater than this quantity, then it will be stable. Now, what do I conclude here? See, k is like the wave number. So inverse of k is the length scale. So the length scale then has to be lesser than inverse of this. So all length scales which are lesser than inverse of this are stable. All length scales which are greater than inverse of this are unstable. Well, that's a criteria that you have already seen before. And I leave it to you to think where you have seen this. And in that case, you have not seen in STAM for the stable case, you have seen for the unstable case. But this is the gist of it. So let me go back a few steps and see what we have done. We started with the fluid equations. And these fluid equations we studied in a very specific form, which is the form, first of all, we considered in a 3D setting, and then we have taken a particular form of the perturbations, in this case linear perturbation, and the perturbations are taken harmonic like this. And for those, I got from the fluid equations the equation for the perturbation, and that requires you to use up the fact that it's a three-dimensional system. And then I use this harmonic perturbation form to get the dispersion relation. I asked the question in the dispersion relation, where is omega square greater than 0? What is the condition that omega square is greater than 0? And that gives me the stability criteria. So this is a completely different scenario than the spiral structures, the density wave theory. But still, it is, I think, very useful to understand what is or how we do the linear stability analysis. Okay, so that is the first 2 points I have written down here. And now let us look at the spiral structures and try to do linear stability analysis of the spiral structure. Well, I'll not go through the entire mathematics. Again, as I said, it's a very complicated one, but I'll give you the essence of it. And finally, write down the dispersion relation, which will tell us where it is stable, where it is not. So how do I go about it? First, we realize that we are dealing with a two-dimensional geometry. It's essentially a disk. So use just polar coordinates, r and phi. And what type of density perturbations we need to choose? Well, remember, the density perturbation is coming because of those rotating ellipses. So I choose the density here. So this is a surface density because it's on a disk. So it's per unit area, mass per unit area. It's a function of r and phi, so which are these coordinates, and time. And how do I make it an ellipse? Well, if this is a constant, that will essentially mean that it's a circularly symmetric one. But I don't want that. I make it a function of r and t. Well, even if it is a function of r, it will still be circularly symmetric. So this gives me the amplitude of the perturbation at a given radius at a given time. And then I introduce the oscillations, which will give me the ellipse structures, or for m greater than 2, it will give me more complicated structures. And the oscillations, I take out this form, m phi plus f r comma t. If you remember from Vidya's class, this is essentially what he was writing down. He did not write down the t dependence explicitly because when he showed the ellipses, he did not show how the star will, how the pattern will rotate. But in this case, we have written down the t dependence also. Now, m, we have already said what it is. Phi is the angular coordinate, the azimuthal coordinate. And this fr gives me the phase of the ellipse. So if I have an ellipse, like this, this is given by fr. This is the fr. Capital R, but anyway. And as you can see, so that is different for different radius. That's why the ellipsis rotates. And that can be different for different time because here we are not in the co-rotating frame. So from the outside of the galaxy, the ellipses are actually rotating. The wave number in this setup is given by del f del r, and the omega, which is the speed of the azimuthal rotation, is given by del f del t. So these things I am not going to show you explicitly, but just take my word for this. Okay, so once we have this, what do? I again write down the continuity equation and the Euler equation in 2D polar coordinate. Put this in the continuity and Euler equation, do the exact same exercise that I did with the 3D case, and then I get a dispersion relation. The dispersion relation looks like this. So let me remind you again what we are doing here. We start with the continuity and the Euler equation, put the in 2D polar coordinate, it's write down the continuity and the Euler equation in 2D polar coordinate, and put this as my perturbation, and that lands me. And then I get the dispersion relation as we have done earlier, and that gives me this. And it has several things, so let me go through them one by one. First, obviously, I have this omega, which is the, what is omega, remember? So this is the oscillation frequency of the perturbation. I'm sorry, just disturb the screen. So it's the oscillation frequency of the perturbation. This is the azimuthal number. So remember, this is in a complete rotation. If I consider, so something is happening here. Let me choose, yeah. So if I am having an ellipse, it is, okay, so this is not a very good ellipse. Let me draw it again. So if I have an ellipse, so this is kind of, these are the two things. So remember that it is a little bit off from a circular disk, circular orbit. The ellipse is just not a circular orbit in this case, and the ellipse is coming to the lower radius here and going to the higher radius here, and it is doing it twice in its entire one azimuthal rotation, lower radius, higher radius, lower radius again, higher radius, lower radius, and that is because m is equals to 2 for the ellipse. Okay. Okay. Now, so that is m. Omega is the circular frequency or the azimuthal frequency. Kappa is the elliptical frequency. K is the wave number. So this is kappa and this is k. They are different. Sigma 0 is some characteristic surface density. It's just like rho 0 before. And sigma is a random velocity component. So this is, I can also think about it as a speed. So this is my complicated dispersion relation. And when will I see that this will give me a stable density wave or a stable spiral structure? When omega square is greater than 0, right? So let us analyze this. When omega square will be greater than 0. First, we take a very simple case where m equals to 0, and that corresponds to a rigid body rotation where kappa is related to omega as kappa equals to omega. This we talked about earlier. So what do? I just put this back in here, m equals to 0, kappa equals to omega. I get a little bit different form of the dispersion relation, which I write, so the right hand side is a function of k only, so I write that as f as a function of k, just for the notation purpose. This is obviously not the same f we saw before. This f is a function of k. Now remember that omega square has to be greater than 0 for stability, and here these two terms are trying to make omega square greater than 0. So this is the rotation and this is the random motion. So both the rotation and random motion try to stabilize the disk. This is the term which is coming because of gravity. You can see this is sigma 0, which is like mass, and this is k, which is 2 pi by lambda, which is like 1 by r. So this is like a gravity term, and this is trying to destabilize the disk. So there's a fight going on between these two. When this will win, then I will have a stable disk. Now, I want stability for all k, all wave number or all uh, wavelengths, all whatever size of perturbation disk I create, I want all of them to be stable. If I want that, that means fk has to be greater than 0 irrespective of all k. Right? Fk greater than 0 means omega square greater than 0 means stability. Now fk is a parabola. So fk, if you want to draw, I'm sorry again. So fk, if I want to draw, it will look like this. It's a parabola. And what is the condition that all points in the parabola, so y-axis is fk, what is the condition that all points in the parabola, all values of fk is greater than 0? Well, when this point is greater than 0. So if this point, which is the minimum of fk, is greater than 0, that essentially means that all fk is greater than 0. And you can find out that condition very easily. So fk minimum will come from del f del k equals 0. That gives me a value of k at the fk minimum, which is equals to this. And I can now use that value of fk minimum and put it back here. Sorry, k minimum, which for a, so this is supposed to be k. So let me just draw it here. This is k. So this is k for fk minimum. So if I put that value of k back over here, then I get for fk minimum greater than equals to 0, this has to be greater than 0. So this has to be greater than 0, which gives me this criteria. So sigma, which is the random velocity components, times omega, which is the rotational velocity components, is greater than the contribution from the gravitational part, then the disk, the disk, the perturbation in the disk will be stable. This quantity has a name, it's called capital Q or Tumre Q, because this stability criteria was first devised by a physicist called Tumre. So this is called the Tumre stability criteria. If you ask the question at solar disk, what is the value of this Q? The value is 1.2. So what do we see here? We see that it is possible to have a completely stable disk, stable for perturbation of all k, all size, when I have both the sigma, the random component, and the rotational component working together. If this part Q is greater than 1, then I will see a stable disk. So I create a perturbation density wave, which is of this type, m equals to 0 type, and that will be stable if this criteria is satisfied. Now I leave it to you as an exercise to see what happens if I choose, say, omega equals to 0. So I have only sigma here, this goes away. Or if I choose only omega, sigma goes away. Can I make a stable disk which is stable for all wavelength perturbations? So that's your exercise. That's your homework. Okay, so this is for m equals to 0. But for a real galaxy, you have at least m less than, m greater than 0. So what happens if m not equals to 0? Well, again, omega square greater than 0 is the stability criteria. So what I do is, first I try to rearrange this, write omega by m as omega p here, and then find out what is mod k in terms of the other things. So I get this. Okay, this is just the same equation written in a different way. And here I have omega p, which is omega by m. So this omega and m are replaced with omega p. And I can again do a little bit of algebra. So I take m by k common, so I get this expression. Now here I see I have written omega, which is the rotational, the tangential rotational, uh, which is the rotational speed, azimuthal angular speed. I'm sorry, azimuthal angular speed as a function of r. This is because remember that you have a rotation curve for the galaxy, and the rotation curve is kind of flat in the outer part of the disk. A flat rotation curve essentially means that omega is changing with r. So this is in general for a galaxy, omega changes with r. So we call a differentially rotating disk. So I can, if I take this part only, set this to 0, then I get this condition that omega r equals omega p plus minus k by m. So if I take the plus solution here, I get a radius for which this condition will be satisfied. Because remember omega, so these quantities are constants, but omega is a function of r. Okay, so k is also can be a function of r. But there will be a r for which omega r will be equals omega p plus k by m. There will be another r for which omega r will be equals omega p minus k by m. So in these two radiuses, these are two extreme radiuses where this part will be 0, which essentially means that k is 0, and k tends to 0 means the wavelength of the perturbation is infinite. So what does it mean? So remember we are plotting this nice wavelength of the perturbation. So this is one wavelength. A little bit larger wavelength perturbation will look like this. And if it's an infinite wavelength perturbation, well, it's not a perturbation anymore, because then it is just like constants everywhere, right? So which means if when this happens, then I don't have the perturbation anymore. So this gives you two radiuses, one inner radius and one outer radius. Inside that, you cannot have this perturbation. So you cannot have a stable density wave or spiral structure. And outside this also, outside the outer radius also, you cannot have a stable spiral structure. These two radiuses are called Lindblad radiuses, and this has a name, it's called Lindblad resonance, where this criteria is satisfied. Okay, this gives us the end of today's lecture. What we have learned is how to analyze the disk. We have seen that a disk is stable when m equals to 0 if you have both rotation and random motion. This will be the case for most of the most of the elliptical galaxies and the bulge in the spiral galaxies. And then we have seen that the spiral structures can exist because this mod k is not infinity inside the two Lindblad radiuses. So spiral structures can exist in a disk, but the spiral structure does not exist below a smaller radius and above a larger radius. So if I have to draw, so I take a smaller Lindblad radius and the larger Lindblad radius, the spiral structures will always exist only between these. There is one more thing which we have not been able to discuss here, is that if we have more than two spiral arms, then you will see that the radius of the inner Lindblad radius, will come somewhere here. So the region over which you have more and more spiral arms will be less and less. So in the initial drawing that I made, the spiral arms were quite long, but if I have the Lindbergh radius bigger, the inner Lindbergh radius bigger, then I will have smaller spiral arms in case of more than two spiral arms. All these are seen in real galaxies. So what I will request you is that you please some of the go through some of the uh, pictures of the Hubble Space Telescope, pictures of the galaxies, and you will see a very nice examples of all that we have talked about here. So thank you. Until next time, goodbye.